Hi Chem 240, it's Dr. Ricardo. This is the fourth video for chapter 13. We're going to pick up in our fourth colligative property called osmosis. So let me describe to you what's happening with osmosis, and then I'll show you the formula that you can use to calculate the osmotic pressure, or to use the osmotic pressure to calculate other things you want to know about a solution. Okay, so here's the concept behind osmosis. In order for osmosis to occur, you need a semi-permeable membrane. So you're thinking down at the molecular level here, right, where this could be a cell membrane, okay? Not so much a cell wall because they're pretty much impermeable, but a cell membrane that kind of had gaps in the molecular structure. So places in the structure that could allow small molecules to go through, but not larger ones. So it's sort of size selective, okay? So osmosis is solvent flow through a semi-permeable membrane to equalize the solute concentration on both sides of the membrane. So the first thing is you definitely need to have these liquids separated by the membrane, okay? Now, if you put the same exact liquid on both sides, you put the same concentration, there's not going to be any pressure buildup on one side or another, because these arrows, if you put the same material on both sides, the arrows going from left to right, which I have here drawn bigger, versus the arrows from right to left would be the same. Okay, so if I had only pure solvent on this side and only pure solvent on this side, there'd be no glucose molecules, everything would be the same, there would be no buildup of osmotic pressure. The key is only the solvent molecules are small enough to go through the membrane. So here's a channel in the membrane, right? A lot of biological systems have membranes in them. All of our cells have membranes in them. They have channels that allow some things to go through, semi-permeable, but not others. Well, guess what? The glucose molecules are way too big to fit through here. They don't have the correct intermolecular properties. Not only is it size, but they may be tend to be very polar, and this membrane may be less polar. So they can't travel through. So what you have is a situation where one side is incredibly organized, right? The pure solvent is identical, 100% pure, but the other side is not pure at all. It's a kind of a mess. It has sugars dissolved in it. Well, since the sugars can't get through the membrane, only the water molecules can get through the membrane. We do have this tendency in nature to equalize everything. We hate it when one thing is perfect and the other thing is a mess. You leave a house, alone for a long time, eventually things start to fall down. Everything starts to, you didn't do anything. There's no energetics involved in the fact that things are going to mix together. There's this natural tendency in the universe for things to become equal on both sides, or to get equally messy, rather than have the left side very, very organized and the right side messy. Both sides will become equally messy, right? So what do we have? We're kind of tricking nature here. That fundamental force, in a way, or that fundamental driving force, is called entropy. Things tend to go to less organization. So even though there's no energetics for the water molecules traveling favorably from left to right, there's an entropy factor. By going from left to right, what's going to happen is they're going to make this side more dilute. And ultimately, they're trying to get closer and closer and closer to pure water. It can never get there, right? Because there's going to still be a little bit glucose, but by the water moving in this direction, it goes from more dilute to less dilute, okay? It goes from incredibly dilute, meaning no glucose on this side. By going over here, you're going to dilute the other side. So that's the driving force. It's an entropy driving force, a messiness driving force. Okay, now, a lot of cool things. I want you to think about grapes, right? So one of the things that you do with your grapes is, when you have grapes, you take them and you keep them wet, right? All of the vegetables at the grocery store, they have misters on them. If you keep your grapes a little bit moist, then what's happening is, first of all, you don't pull the grapes off of the because you break the bond, you break the seal, right? So you keep your grapes nice and tight on the vine, okay? And if it's wet on the outside of the grape, the skin of the grape is a cell membrane. Water can get through, but the sugars can't get out. So if the grapes are wet, you're going to keep them nice and plump because water is going to keep on going through the membrane by osmosis and the sugar can't escape. So that's the reason to keep your vegetables moist or your lettuce moist, is this idea of osmosis going through the membranes of the grape. So there's the skin of the grape. Water can get in. Glucose can't move that way. So the skin, the grape here, is going to become more plump and beautiful and more tasty because it's going to have more water in it. Opposite is when you make raisins. You make raisins on purpose by allowing the water to leak out when you have like sun-dried, or you can make this more sugary on the outside, and then the raisins will contract this way if it's very sugary on this side, if the concentration is bigger on the other side. So we'll talk about that in a minute. Okay, so that's what's happening. It's a difference between the pure side and the solution side. That's osmosis. The driving force is always to go from the solvent molecules, go from the less dilute side, from the more dilute side to the less dilute side. So pure is the ultimate dilute. So pure would definitely go this way. And only the waters can fit between the membranes. Here's the formula, okay? So the osmotic pressure is a colligative property of a solution equal to the pressure that when applied to the solution just stops osmosis, okay? So the osmotic pressure in my picture back here would be the amount of pressure I would have to push in on this liquid and force this liquid into the membrane on this side so that I could balance these forces and they would become equal. So how much pressure do I need to apply is the osmotic pressure, okay? If I apply that pressure and I squeeze this liquid in, I have this in a syringe on the membrane and I squeeze this side in, I can stop osmosis. If I put more pressure than that, I can actually create reverse osmosis and force the water in the direction that it doesn't want to go, against nature, and take water out of this concentrated side and push it in the other direction. So that's one way to create pure water from salty water. Some desalinization plants use reverse osmosis, where you put pressure on the salty water to force fresh water out the other side. But that takes a lot of energy to keep that pressure up. So you have to burn a lot of hydrocarbons. So in countries that have more oil and gas than they do fresh water, like Saudi Arabia, at the refineries, many times while they're doing the refining, they use some of the fossil fuels to generate water for their society. Okay, because you need water is just as important. So if you're in a desert community, you can use reverse osmosis. Okay, so osmosis naturally goes this way. Reverse osmosis is you push the pressure back the other way. Okay, here's the formula, and then I'll show you a couple of other cool things from the book. Okay, so now the osmotic pressure is equal to the symbol pi. It's got nothing to do with circles, okay? It's just the same unit, okay? It's just the same variable, okay? So the osmotic pressure is the colligative property of a solution equal to the pressure that when applied to the solution just stops osmosis. The osmotic pressure then is equal to the molarity with a capital M, the moles per liter of the solute in the solution, okay? Multiplied by the gas constant. This time you're going to use the gas constant in the way you learned it in chapter 10, 0.082 liter atmospheres per mole Kelvin. That's the version of R that you need, times the Kelvin temperature. So just 3 factors. Okay, if you're at constant temperature, this one doesn't change anything. But the key thing is the osmotic pressure is directly proportional to the molality of the solute. So back to our glucose solution, whatever the concentration is of the glucose here, that's going to make the osmotic pressure bigger. Okay, the sugary this solution is, the higher the pressure I'm going to need to stop this process from happening. Or another way to say it is, the more expectation, the pressure of the water leaking through the membrane will be greater, the bigger the difference in the concentration. If you had the same sugariness on one side and the other, the difference in the molality would be zero, so the osmotic pressure would be zero. So this you could either think of as what is the molality of one side when the other side is zero, or what's the molarity difference between the two sides. Okay, so we have a big molarity difference. This one is zero, has zero solute in it. This one is whatever the molarity is. Okay, so pretty easy to use that equation. Okay, this guy is going to come out in atmospheres of pressure, right? This guy, moles and liters will cancel out with molarity, and Kelvin will cancel out. So expect this osmotic pressure to come out in atmospheres. Okay, this is the molality of the solution. What does nature do? Nature is more interested in going from the more dilute to less dilute. Okay, more dilute means more pure. Okay, desalinization is reverse osmosis. If the external pressure that I push on with my syringe or whatever force that I'm putting on is greater than the osmotic pressure, okay, then I can push it in the other direction. So this would be an example. Here's my membrane set up. If P, the external pressure, is less than the osmotic pressure, then I'm going to have osmosis. I'm going to have water molecules leak. Water molecules are just in the background here. I didn't color them in, okay? The dots are the solute. So I'm going to have water come this way because remember, those X's are too big to make it through those channels. If I push in to the point with my external pressure that the external pressure is equal to the pressure of nature trying to leak through, because we don't like one side to be pure and the other side to be unpure, that would be at equilibrium. That would be, I would get nothing happening, right? There would be the same amount of movement of water in this direction as that direction. And reverse osmosis is if I squeeze the salt water or the sugary water so much on this side and put such a high external pressure here that I force water through those spaces. Because remember, the solute is too big to get through. That's reverse osmosis. So I can make pure water out of water that has solvents in it. So I can take salty water and make it pure water. Some people have reverse osmosis in their home. That's what you do. You use the external water pressure that's provided by the company to push, right, the pressure of the water that's coming through the pipes, to push in on a membrane inside this cavity and slowly leak pure water out. Okay, it's a slow process. So the more surface area of membrane you have, the more water you can generate. The more surface area of membrane, the more external pressure you're going to have to put. So this takes a lot of effort. Okay, you can create small amounts of drinking water, enough for your house, because it's constantly making it just from the pressure that the water pressure comes in at. So if you don't like your water in your house, you think it's got too many ions in it, you don't like the taste or something, you can buy one of these things at Home Depot that uses reverse osmosis to make pure water. Okay. Okay, last three topics. I'm not going to go into any detail here. I'm going to cover them exclusively when we go through the PowerPoint. So we'll talk a little bit about colloids, which are not truly solutions, okay? Examples of colloids are aerosols. That is, aerosols are droplets of a liquid in a gas state. Emulsions, right, which is like when you take oil and vinegar and mix them up, or mayonnaise is an example of an emulsion. That's a liquid. And a sol or a sol gel, that's when you have a solid in a liquid. Example of a sol is the display on your calculators, right? This is solid. Those little bars in there are if you can get a magnetic solid to line up in such a way that it creates that little effect that you have. So these are actually an example of a sol. It's a solid in a liquid, okay? So colloids are bigger groups, hundreds, thousands of one thing in the other, right? An aerosol would be liquid in a gas, emulsion would be a liquid in a liquid, mayonnaise, and a sol would be like your calculated display, solid particles in a liquid, okay? Then we're going to talk about association colloids, of which there are two really cool types that we see in biology a lot, and one of them are called micelles and the other one are called vesicles. Okay, so these are droplets inside a liquid, probably on the order of thousands of molecules like a cell membrane that organize in tiny little droplets. And the beauty of these micelles that happen in nature is you can hide things in them. So if you want to get a medicine into someone's body and the body does not really have a natural absorption for that size and shape of molecule, you can put it inside of micelles, and the micelles will be absorbed into the body, and then once they're in the bloodstream, they'll break down and release the medicine. So it's a way to time release a medicine into the body, is you can put them into micelles. Okay. Also, micelles, vesicles are very similar to micelles, only instead of just being round, like this, right, where all of the molecules that we're interested are kind of all lined up around the outside, and we can hide our medicine in here. What a vesicle is kind of like a donut. And all of the stuff that you're interested in is in here, like just like a donut, right? Like a round donut. So they just happen to be, instead of just big meatballs of material, they happen to be shaped like this. So some kinds of soaps and detergents are vesicle formers, some kind are micelle formers. What's the material that I'm talking about? One type of chemical that does not like to dissolve in another. So if this was in water, you might have all different molecules kind of arranged like this, where all the molecules pack together to make these superstructures. So I'll talk about them a little bit more. Okay? And lastly, how does soap work, or how does detergent work? Soap is a micelle former. So I'll explain how you remove the dirt from your skin or clothes by using micelles. Where does the dirt go, and how does it get carried out of the clothes or out off of your skin and down the drain? Okay, so that's it for the last video of chapter 13. Okay, I might make one special video. Wait, I might as well show you this while we're here. This is from your book. This is a red blood cell. This sort of started taking the shape of a vesicle. Okay, you can sort of see the puncture coming out. And this guy would be more of a micelle, where they're round like that. Okay. See if I show you some more examples. So here's a micelle where the individual molecules are kind of create the whole effect and how you carry oil outside of the body. Okay, I'll do this more in lecture. And the last cool thing that you can get out of here is if you just think of the natural pressure, if you put your semi-permeable membrane, this is for osmosis, okay? So on this side you have just solvent particles. Here you have the semi-permeable membrane, and you have the blue stuff is the dissolved things. So initially, you put it in on both sides, okay? And the pressure from the weight of the liquid is the same because the level is the same, okay? Come back a few hours later, and since it is only the solute molecules that are small enough to move through the semi-permeable membrane, they go this way, but they're not counteracted to the same degree by them traveling across. So this side goes down and this side goes up. Okay? When I reach equilibrium, I get to the point where the height of this column stops going up. So this has a higher height, right? It's not the bent part, it's the height. So there's more gravity, right? There's more mass times, what would be the force on this? Would be the mass times the acceleration due to gravity on this side compared to that side. So there's an uneven balance, right? So if I measured this height, I could, just from that height, I could calculate what the what the osmotic pressure is. Last thing I could do is I could put an external force on this side, nice and slowly, and push this side back down to where I equilibrated it. And that external force now, see how they're tied here? They're tied here. This comes to equilibrium, right? What's providing the extra force here that makes it not continue to undergo osmosis? Well, the weight of this extra liquid on this side is now pushing down more on one side than another. It's not balanced. So that's why osmosis can't continue anymore, because I have this weight. Well, another way to do that is just push in on the liquid, push it through the membrane back the other way, and now that osmotic pressure, that amount of pressure that you have to put on here, is the same as the pressure provided by the extra layer of water. So here and here, these are both at equilibrium. Okay? Here's the process is just starting, so you're out of equilibrium until the two sides become equal. The forces become equal. Force is equal here, force is equal here, the force is not equal yet. Good? All right, let's take a break right there. That's everything for osmosis. Good.